So if NB is greater than Na, it is stable, and if Na is greater than NB, the molecule will be unstable. If both the electrons are present in it, that is if the electrons are paired, and in the whole molecule if all the electrons are paired, then we can say that it is a diamagnetic molecule. Helium exists as monoatomic. It can exist as helium atom, but it can't exist as helium molecule. Hello everyone, this is Ambli Unnikrishan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. Last session, we discussed about the hybridization involving S, P and D orbitals, right? Then we discussed about the limitations of valence bond theory, and then we started off with the next approach to chemical bonding, that is molecular orbital theory, right? Yes. So in today's session, we will be discussing about, yes, electronic configuration, and from that how you will be able to predict the molecular behavior, right? And then bonding in some homonuclear diatomic molecules we will be studying, and then last topic is hydrogen bonding, right? So beginning with the first one, that is electronic configuration and molecular behavior. So till now in molecular orbital theory we studied, yes, the atomic orbitals are combining and they form molecular orbitals. Yes, so in the case of molecules, the electrons are present in molecular orbitals, right? And we also studied how to represent these electrons, yes, how to fill the electrons in the molecular orbital diagram using molecular orbital diagram, right? So we know that when two atomic orbitals are combining, they form two molecular orbitals, out of which one will be bonding molecular orbital and the other one will be anti-bonding molecular orbital, right? So using the electronic configuration, we will be able to predict the molecular behavior. So in detail, we will be studying about the stability of the molecules, right? And then bond order. We know what is bond order. In the last chapter also we have studied what is bond order, right? And then we will be discussing on the nature of the bond, bond length and the magnetic behavior. So the first one is stability of the bond. So calculating or by understanding the number of electrons which is present in bonding molecular orbital and anti-bonding molecular orbital, we will be able to predict the stability of the molecule. Right? So, if NB is the number of electrons which is occupying bonding molecular orbital, right? So, if NB is the number of electrons present in bonding molecular orbital and Na is the number of electrons which is present in, yes, anti-bonding molecular orbital, then the molecule, if we know the number of electrons which is present in bonding molecular orbital and anti-bonding molecular orbital, we can predict the stability. That is, if the molecule is stable, then NB will be greater than Na, right? Bonding molecular orbital, right? That takes part in the bond formation. So, if the number of electrons which is present in bonding molecular orbital is greater than number of electrons which is present in anti-bonding molecular orbital, yes, we can predict that the molecule will be stable, right? And in the opposite way, if the molecule is unstable, if Na is greater than Nb, that is if the number of electrons present in the anti-bonding molecular orbital is greater than number of electrons present in bonding molecular orbital, then we can predict that the molecule is unstable. Yes, so I hope it is clear from the electronic configuration, that is by understanding the number of electrons present in bonding molecular orbital and anti-bonding molecular orbital, we will be able to predict whether the molecule is stable or unstable. So if NB is greater than Na, it is stable, and if Na is greater than Nb, the molecule will be unstable. Now moving on to the next one, that is bond order. Right? So, how do you calculate the bond order? The equation for calculating it is half of the number of electrons which is present in bonding molecular orbital minus the number of electrons present in anti-bonding molecular orbital. So, we know that what did we study about bond order? Yes, it is the number of bonds between two atoms. Right? See, if we say it is single bond, then the bond order is 1. If it is double bond, the bond order is 2. If it is triple bond, the bond order is 3. Right? So, how do you calculate the number of bonds? Yes, that is a bond order. How do you calculate it? Using this equation, right? That is half into number of electrons which are present there in the bonding molecular orbital minus number of electrons present in antibonding molecular orbital. So that is equal to half of Nb minus Na. Nb represents the number of electrons in bonding molecular orbital and Na number of electrons in antibonding molecular orbitals. So a positive bond order, right? That is Nb, if Nb is greater than Na, then if we take the difference of Nb and Na, we get a positive value, right? So if you calculate the bond order and if you are getting a positive value, we can predict that the molecule is stable, right? And if you are getting a negative value or zero value, yes, negative or zero value, that is when Na is greater than Nb, yes, that means the molecule is unstable. The bond order is 0 means a bond is not even formed there. So in that case, how can you say the molecule is stable, right? So the molecule will be unstable. So using the bond order also you can predict the stability, right? How to calculate bond order? Using this equation. And if you get a positive value, we can say that the molecule is stable. And if you get a negative or zero value, the molecule will be unstable. So if you can calculate the bond order, how will the bond length change according to it? Yes, the bond length decreases as bond order increases. We already know that if a single bond is present, it will have the highest bond length. Then comes double bond and then triple bond, right? So the highest bond length will be for single bond and the bond length will be the least for triple bond, right? So bond length and the bond order is inversely proportional. So if bond length increases, the bond order decreases. I hope it is clear. So now moving on to the next one, that is magnetic behavior. So if all the electrons are paired, then we say that the molecule is diamagnetic. So if in an orbital, we know that yes, only 2 electrons can be accommodated in a single orbital. So if both the electrons are present in it, that is if the electrons are paired, and in the whole molecule, if all the electrons are paired, when we can say that it is a diamagnetic molecule. And if there are unpaired electrons present in an orbital, if yes, only one electron is present in there and no other electron is present to pair it up, yes, we say that there are unpaired electrons, right? So if unpaired electrons are present, yes, the molecule will be paramagnetic. Yes, so if all the electrons are paired, it is diamagnetic, and if it is unpaired, it is paramagnetic. Now, what is diamagnetic and paramagnetic? Yes, diamagnetic substances are repelled by magnetic field. Okay, so when an external magnetic field is applied, it repels it. Right, and paramagnetic molecules, they attract the magnetic field. So when an external magnetic field is applied, it attracts the magnetic field. Okay, yes, so that is diamagnetic and paramagnetic. So based on the number of electrons, yes, the electronic configuration, we will be able to predict whether the molecule is diamagnetic or paramagnetic also. Right, now moving on to the next topic, that is bonding in some homonuclear diatomic molecules. So we will be studying about homonuclear diatomic molecules. So that means yes, homonuclear, both are same atoms present, and diatomic molecules, that means 2 atoms will be present, right? So we will be specifically discussing about some specific diatomic molecules here and the electronic configuration of them and how the bonding is present, the bond order, and from which we can predict which and all informations, all that we will be discussing for certain molecules, right? So the first one is hydrogen molecule, right? That is H2. Now it is formed by the combination of 2 hydrogen atoms. Right, 2 hydrogen atoms combined, they form hydrogen molecule. And each hydrogen atom has 1 electron in its 1s orbital. Therefore, in all, there are 2 electrons in hydrogen molecule which are represented in sigma 1s molecular orbital. Yes, so from the diagram you can see, yes, 2 hydrogen atoms, they combine and form a hydrogen molecule. So this is the 1s orbital of one hydrogen atom. This is the 1s orbital of another hydrogen atom. Okay, now they combine and form the molecule. So we know that when the atomic orbitals are combining, it forms 2. Yes, 2 atomic orbitals are combining. 2 molecular orbitals will be formed. So this 1s and 1s combines and form yes, sigma 1s and sigma star 1s, right? Bonding molecular orbital and anti-bonding molecular orbital. So this is sigma 1s and sigma star 1s. So we know that in this hydrogen atom, 1 electron is present. In this hydrogen atom, 1 electron is present. So a total of 2 electrons will be present in the molecule, right? So we know that, yes, according to the rules which we have studied, first the molecular orbital with the lower energy gets filled. So the 2 electrons get filled in sigma 1s orbital, right? So what will be the electronic configuration of the H2 molecule? It will be sigma 1s2. Right. So in the sigma 1s molecular orbital, there are 2 electrons. So how do I represent sigma 1s2? So this is a, yes, electronic configuration. Yes, I hope from where this sigma 1s2 came, it is clear for you. Now, the bond order for H2 molecule can be calculated as given. We know the equation for finding the bond order. It is half of Nb minus Na. So in this case, yes, the number of bonding molecular orbital electrons are 2. Right. In the anti-bonding molecular orbital, is there any electrons? No, right? It is 0. So half of, it becomes half of 2 minus 0. That is 2 by 2, it will be equal to 1. So if the bond order is equal to 1, that means a single bond is present, right? So the hydrogen molecule, yes, in hydrogen molecule, the hydrogen atoms are bonded by a single bond. I hope it is clear. From the bond order value, you can understand that concept as well. Yes. So hence H single bond is present in hydrogen molecule. And this means that the 2 hydrogen atoms are bonded together by a single covalent bond. And since no unpaired electrons is present, it is therefore a diamagnetic molecule. Even that we can understand, right? In this molecular orbital, both electrons are paired. In this, no electrons are present. So whatever electrons are present, they are paired. Yes, no unpaired electrons are present, so the molecule will be diamagnetic. So this is the bonding in hydrogen molecule. So now moving on to the next one, that is helium molecule. So in the case of helium, we know that the electronic configuration of helium atom is 1s2. It contains 2 electrons, right? So in this 1s orbital of one helium atom, 2 electrons are there. In the 1s orbital of another helium atom, 2 electrons are there. Now the atomic orbitals combine and form 2 molecular orbitals, sigma 1s and sigma star 1s, right? So yes, now a total of 2 plus 2, 4 electrons are present in the He2, helium-2 molecule, right? So 2 electrons, first it gets filled in sigma 1s orbital and then it moves to the higher energy one, that is the anti-bonding molecular orbital, and it fills sigma star 1s orbital also. Clear? So 2 in here and 2 in there. Okay. So what will be the electronic configuration? It will be sigma 1s2, sigma star 1s2. In sigma 1s 2 electrons, sigma star 2s 2 electron. Yes. So this is how you can represent it. Clear? Now coming to the bond order. How do you calculate it? Same equation. Half of Nb minus Na. So how many number of bonding electrons are there? Bonding molecular orbital, how many electrons are there? 2, right? Yes, sigma 1s 2 electrons are there. So half of 2 minus, right? 2 minus how many number of electrons in anti-bonding molecular orbital? 2 again. So it is half of 2 minus 2. 2 minus 2 is 0. So 0 by 2 is again 0. Right? Yes. So the bond order is 0. That means, yes, the molecule is unstable. Right? So the molecule doesn't exist. Right? If there is no bond order is 0 means it doesn't form any bonds. So that means the molecule is not existing. Yes. And it is monoatomic. So helium exists as monoatomic. It can exist as helium atom, but it can't exist as helium molecule. So now moving on to the next one, that is lithium molecule. Right. So the electronic configuration of lithium atom is, we know that it is 1s2, 2s1. Right. 3 electrons a total. So 1s2, 2s1. And there are 6 electrons in Li2. Right. In lithium molecule, there will be 6 electrons. Right. So as you can see here, right, in the 1s orbital, right, of one lithium atom and the 1s orbital of other lithium atom, the atomic orbitals, they combine. And then they form 2 molecular orbitals, sigma 1s, sigma star 1s. So, yes, a total of 2 plus 2, 4 electrons, which gets filled in sigma 1s and sigma star 1s. Now, moving on to the 2s orbital, in which 1 electron is present. In this lithium atom, 1 electron is present in 2s orbital, and here also 1 electron. Now, a total of 2 electrons are to be in the molecular orbital. Yes, that 2 electron gets filled in the bonding molecular orbital, and in the anti-bonding molecular orbital, nothing gets filled. So this is clear, the molecular orbital diagram. So from this, again, you will be able to calculate the bond order. It is Nb minus Na by 2. right? So how many number of bonding molecular orbital electrons are here? It is 1, 2 and 3, 4, right? Yes, so half of 4 minus, right? Now how many number of anti-bonding molecular electrons are there? Yes, that is 2. Right, in the sigma star oneness there is 2 and sigma star 2 is no electrons, right? So it is 2. So 4 minus 2 is 2, 2 divided by 2 is 1. So the bond order is equal to 1. So here also we understood that a single covalent bond is present, right? So this means that molecule is stable, and since it has no unpaired electrons, it should be diamagnetic. That is also clear, right? Are there any unpaired electrons? No, right? Here, here and here all of them are paired electrons. So that means it is a diamagnetic molecule, right? Clear? Now moving on to the next one, that is carbon molecule, C2 molecule. So in this case, we know that the electronic configuration of one carbon atom is 1s2, 2s2 and 2p2. The atomic number is 6, right? So 1s2, 2s2, 2p2. That means a total of, yes, 6 electron. Now, in the other carbon atom also there is a total of 6 electrons. That means the carbon molecule, that is C2, will have a total of 12 electrons, right? So, what will be the electronic configuration? Let's see here, okay? So, beneath this, the sigma oneness, that means the two oneness orbitals are also present, right? Because they are completely filled, at times we need not represent it, okay? Yes, so sigma oneness, that is the oneness orbitals of each of the carbon atom, they overlap. The atomic orbitals overlap with each other and form molecular orbitals. Yes, they combine and form molecular orbitals. Sigma 1s and sigma star 1s, which is completely filled. Now moving on to the 2s. Yes, so in 2s, how many electrons are present? In each of the carbon atom, 2 electrons are present. So one carbon atom, 2 electrons, and in here also 2 electrons. Now a total of 4 electrons are to be filled. So sigma 2s and sigma star 2s. Yes, 2 electrons get filled here and then 2 in the sigma 2s orbital. Right. Now coming on to the 2p. What is the electronic configuration? 2p, 2 for each carbon atom. So 2 electrons here and 2 electron here in the p orbital, right, for each carbon atom. And then yes, it combines and form the molecular orbital. So px and py, they combine form pi molecular orbital, right? So yes, the order for filling of the electronic electrons in the molecular orbital we have studied. So for C2, it will be, yes, pi 2px is equal to pi 2py, then sigma 2pz, pi star 2px is equal to pi star 2py, then sigma star 2pz. Okay, so a total of 2 and 2, that is 4 electrons to be filled here. So 1, 2 and 3, 4. So it all gets filled in the pi molecular orbital itself. That is pi star 2px is equal to pi star 2py. So yes, I hope it is clear. So what will be the electronic configuration? It is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2 and pi 2px is equal to pi 2py, in which on both of the orbital 2 electrons are present. Pi 2px2 is equal to pi 2py2. Okay, yes, so from here itself you can understand there are no unpaired electrons present. All the electrons are paired here. So of course the molecule will be diamagnetic. And we know how to calculate the bond order. Again, it is half of Nb minus Na. So how to calculate the bond order? It is half of Nb minus Na. So how do you calculate Nb? The number of electrons present in bonding molecular orbital. So below this, in this diagram, below this, the oneness orbitals are also there, right? The sigma 1s and sigma star 1s. So including that here, right? So how many number of electrons in bonding molecular orbital? It is 2 plus 2 plus 2 plus 2. That is 8 electrons total, right? 8 minus number of electrons in anti-bonding molecular orbital. That is again 2, yes, 2. That is 4. Okay, 2 plus 2, that is 4. 8 minus 4 is 4. 4 divided by 2 is 2. Yes, okay. And C2 should be a diamagnetic molecule because it is having no unpaired electron. And we understood it is a bond order is equal to 2. That means there is a double bond which exists between the two carbon atoms. And what you have to remember here is that from where this double bond is coming. See, as you can see here, the last 2 electrons, the last 4 electrons which is present in the bonding molecular orbital, it is from the pi, right? Pi 2px and pi 2py, right? So, both the double bonds, that is, the both bonds which is present, it is contributed by the pi. Right. So what did we usually study? out of the double bonds which is present, one will be sigma and the other will be pi. So in the case of C2, both are contributions of pi. Okay, that is both are pi bonds. I hope it is clear. Now moving on to the last diatomic molecule, that is oxygen. Okay, so in the case of oxygen, the electronic configuration of oxygen atom in its ground state is 1s2, 2s2, 2p4. Atomic number is 8. So 1s2, 2s2, 2p4. Right. Now each oxygen atom has 8 electrons in total. So how many electrons will be there in oxygen molecules? 8 into 2, that is 16 electrons will be present. Right. So as you can see in the molecular orbital diagram, yes, below this again, the 1s orbital is completely filled, that is sigma 1s and sigma star 1s. So we are not representing it. Now coming on to the 2s. Right. So in 2s, 2 electrons of each oxygen atom. So a total of 4 electrons present. So in this case also, below this, the 1s orbitals are also present, right? They form sigma 1s and sigma star 1s molecular orbitals which are completely filled. Now coming on to 2s, right? Here in one oxygen atom, 2s is filled with 2 electrons and here also 2 electrons. Now a total of 4 electrons to be filled, which is filled in sigma 2s and sigma star 2s. Now coming on to the p orbital. In the 2p orbital, right, one oxygen atom is having 2p4, right? 4 electrons here and 4 electrons here. So a total of, yes, 8 electrons need to be filled in the molecular orbitals. So 1, 2, 3, 4, 5, 6 and 7, 8, right? How it gets filled? 1, 2 here in the lowest energy level and then, yes, singly filled first, then they get paired up, right? We know that, right? According to the rules. Yes, so first they are singly occupied, then it pairs up. Now the other last 2 electrons to be filled, they are singly occupied in each of the orbital. Yes, they do not get paired up because we know that, yes, first the orbitals having same energy, electrons must be singly occupied, then only it starts pairing. So each of the electrons will be singly occupied. I hope it is clear. So this is the molecular orbital diagram. Now, what will be the electronic configuration? Yes, it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz square. Yes, sigma 2pz2 and then pi 2px is equal to pi 2py. And yes, in that case, both are completely filled and the pi star molecular orbital, it is singly filled. Yes, I hope it is clear. So now the order for oxygen and fluorine molecule we have studied. So in case of oxygen and fluorine molecule, this is the order. And in case of other molecules, yes, the sigma 2pz comes on the top and pi 2px is equal to pi 2py comes below. Yes, I hope it is clear. Yes, now from this we can calculate the bond order. It will be again half of Nb minus Na. So what is Nb? It is 2 plus 2. Yes, the bonding molecular orbital. 2 plus 2. Plus in the sigma 2pz again 2, here also 2 and 2. Yes, this is the anti-bonding molecular orbital wherever the star is present, right? So, yes, that is half of 10 minus number of electrons in anti-bonding molecular orbital. It will be, yes, 2 plus 2 and here 1, 1, that is 2. So, it gives a total of 6. Yes, 10 minus 6 is 4, 4 divided by 2 is 2. Okay, yes, so the bond order is 2, that is between the 2 oxygen atoms, yes. A double bond is present and which is contributed, both of them is contributed by the pi, right? Yes, and then oxygen molecule is paramagnetic. It is not diamagnetic, it is paramagnetic. Why? Because is equal to sigma star 2py, we can see there are unpaired electrons present there. They are not paired, right? So wherever there is unpaired electrons, it is a paramagnetic molecule. So oxygen molecule is a paramagnetic molecule. I hope it is clear, right? Yes, so that was about the discussion of different homonuclear diatomic molecules and the bonding present in it, right? So from the electronic configuration, we were able to calculate the bond order and predict whether, yes, they are stable or unstable and predict also their paramagnetism or diamagnetism, right? So I hope all the diatomic molecules that we have discussed is clear for you. The bonding is clear, right? Now coming on to the last topic, that is hydrogen bonding. So what is hydrogen bonding? When a highly electronegative element like nitrogen, oxygen or fluorine are attached to hydrogen to form covalent bond, the electrons of covalent bond are shifted towards the more electronegative atom. Yes, so the partial positive charge developed on hydrogen atom forms bond with the other electronegative atom. So, hydrogen bond is basically a bond which is formed between the hydrogen atom and an electronegative atom. Yes, so as you can see here, in this case of water molecule, yes, one H2O here and one H2O here, right? So, there is an electronegative difference between the hydrogen and the oxygen atom. So, we know that, yes, the covalent bond which is present between the hydrogen and oxygen, that is the shared pair of electrons will have a, yes, that is the shift or gets attracted towards the more electronegative atom. So, in this case, out of hydrogen and oxygen, yes, that is the shared pair of electrons will be more attracted towards oxygen. So, the oxygen attains a partial negative charge and hydrogen is having a partial positive charge. Now, this hydrogen atom and the electronegative atom which is having a partial negative charge. So, now there is a bond which is formed between them. Yes, which is represented by this dotted line. That is called as hydrogen bonding. So, it is a bond between hydrogen, yes, that is the partial positive charge developed on the hydrogen atom forms bond with the other electronegative atom. So, the partial positive charge which is attained by the hydrogen atom, yes, it forms the bond with the other electronegative atom. So, this is called as hydrogen bond. Okay. Now, there are two types of hydrogen bond as well. It is intermolecular hydrogen bond and intramolecular hydrogen bond. Yes. Okay. So, there is a difference between inter and intra, right? So, intermolecular hydrogen bonding is between two different molecules. A hydrogen bond is formed between two different molecules. And intramolecular hydrogen bond means it is formed within a molecule. Right? So, if it is formed between two different molecules of the same or different compounds, it is intermolecular hydrogen bond. Right? We say inter-college fest, inter-school fest. Right? So, that is between two colleges or two schools. Right? So, that is intermolecular. So, intermolecular means it will be between two molecules, separate molecules. Right? So, there is one HF molecule here and one HF molecule here. Right? So, what happens? Yes, the fluorine atom, as it is more electronegative, it attains a partial negative charge and the hydrogen will be having a partial positive charge, right? So, this hydrogen and the fluorine of another molecule, they have a hydrogen bond between them which is represented by this, yes, dotted line. So, this hydrogen bond which is formed between hydrogen and the electronegative atom of another molecule is called as intermolecular hydrogen bonding. Now, coming on to intramolecular hydrogen bonding, that is formed within a molecule. It is formed when hydrogen atom is in between the two electronegative atoms present within the same molecule. So, it is formed when hydrogen atom is in between two electronegative atoms which is present in the same molecule. So, in this molecule you can see, yes, it is formed between two electronegative atoms. So, as you can see here, yes, the hydrogen is present in between two electronegative atoms, that is these two oxygen, right? They are more electronegative than hydrogen. So, a hydrogen bond will be formed within this molecule, right? A hydrogen bond will be present between the oxygen and hydrogen atom. So, that is intramolecular hydrogen bonding. So, I hope hydrogen bonding, intermolecular and intramolecular hydrogen bonding is clear for you. So, intramolecular, it will be within a molecule and intermolecular, it will be among two different molecules. So, by this we come to the end of this chapter, right? So, the chapter is quite lengthy. So, I hope all the concepts that we have discussed in this chapter is clear for you. So, that's all for today. Thank you.